So welcome back to our physics content. This time talking about the refraction of light. This lesson includes several titles like the light and the boundaries, Snell's law of refraction, the meaning of the index of refraction, then the total internal reflection, and at the end talking or discussing the mirage effect. Of course, it will include all applications in between. Alright, so here we go. So this is according to Glencoe physics book. This is chapter 18. This chapter includes 3 sections. Today we'll be talking about the refraction of light. After that, the convex and concave lenses, and we finish by discussing the application of lenses. So here we go. This lesson starts by defining the light and boundaries. So also, as a continuation of the reflection of light, we're still studying the light behavior when it hits a boundary or hitting a matter. So in this case, so when the light crosses a boundary, okay, as we see here, when the light crosses a boundary between two mediums, it bends, as we see here in this picture. Okay, when the laser light, first starting from the air, enter a different space or enter a different medium, okay, what do you notice about the light? It's bending a little bit, it deviates from its main direction. So this is what we call by bending of light, okay, when the light passing in between two mediums. Okay, here is another example. Okay, so that's how we define refraction, by the way. Okay, due to the bending of light, the boundaries between two mediums. So here as well we have two mediums. Let's say we have the air medium and here we have the water medium. Okay, so when that water, when the laser light or the object pass from one place, let's say the air to the water, okay, from one medium to another, this is called as refraction. Okay, we're not talking about reflection of light. This time the light continues through the other medium, and this is why, and this is how we define refraction of light. Okay, here we have different mediums. So let's start with the figure, then we go to the text. So we have a laser of light, okay, passing through different mediums. Okay, it's the same light passing through the 3 different mediums, as you see here. So in the first case, the light crosses the water boundary. So here we have a water medium, the same light passing, hitting the boundary of the glass. So it's an air glass medium. And then at the end from the air, and then it bends and enters the medium of the diamond. Alright? So in this case, what are we getting from this? In all cases, we have refraction of light, of course. But as you notice, the deviation of the light differ from medium to another. So let's say the deviation of the light when passing through the water deviate a little bit. As you see, it was the light going that direction, and it changed direction a little bit. If you compare that to the diamond, if you see here, the light was passing through, and then by hitting the boundary, it deviated a lot, changed direction a lot. So we'll be discussing about that, but in all cases we're still talking about the refraction. Okay, so what to get from this text? So so here in this text they are introducing to us what they are just trying to explain in this figure. So the light hits the surface of each medium at the same angle. So it's the same light and the same angle hitting the boundary each time. Okay, so the light rays bend more the bend is not constant in all mediums. So this deviation of the angle depends on the medium itself. So this depends on the properties of the medium itself. So we'll be discussing about that later in this chapter. But just to mention at the time that again we have the same incident light crossing 3 different boundaries, but the behavior of the light is different every time. Here it's bending a little bit when passing through the water. However, here in the diamond, it's bending more of that. All right. We continue. So, starting here with talking or discussing the Snell law. Okay, Snell is the name of the person who, with René Descartes, okay, they try to describe the refraction phenomena. Okay, so what happens first? So they measure two angles, as we see here in this figure. So we have the light first, okay, hitting the boundary. This is what we call the first boundary. Of course, the light will refract, okay, enter the second medium. Okay, so we have another angle. So the first angle we call the angle of incidence, θ1, and we have the second angle, okay, as you see here. It's not the same angle, huh? Okay, θ1 is different than θ2. θ2 is deviated more from the normal, so we are describing here two different angles. So they measure, René Descartes and Snell, both of them, they measure two angles. Okay, so what they noticed? So they noticed that the incident θ1, okay, the main angle θ1 here, this is the main angle θ1, is the angle at which the light strikes the surface. So it's hitting the surface, that's the surface, let's say, separating air from water. Okay, so that's the surface. Okay, so the angle of refraction θ2, this is θ2 by the way, okay, is the angle at which the transmitted light leaves the surface. So this angle, when the light leave this surface, that's what we mean by θ2. So what did we find out from this Snell law? So they describe something called the index of refraction. Index of refraction. This means that every medium has its own index of refraction. So let's look at this table that you have it in your book, by the way. So we have the index of refraction in case of vacuum, and in case of the air it's approximately 1. N is equal to 1. N represent what? N represent the index of refraction, or describe how much the deviation from one medium to another medium. Again, so the index of refraction describe, okay, how much the main or the light will deviate when passing to another medium. Okay, so the index of refraction, N, determines the angle. Okay, so it's determining the angle when the light, okay, as it crosses the boundary between two mediums. So again, let's go back to the table itself and let's look at this one. So in case of vacuum and in the air, N, which is the index of refraction, is equal to 1 approximately. In case of water, as you see here, N starts to get bigger and bigger. It's 1.33. In case of a glass, 1.52. In case of quartz, 1.54. And in case of diamond, it's 2.42. If you notice in the first slide, we described the deviation in the diamond, the light. When it crosses the diamond, it deviates more. Why is that? Because we have in diamond, the index of refraction is 2.42. It's way higher when compared to the index of refraction in case of vacuum or in the air. Okay, so this is a Snell law. This is a Snell law according to his name. So we have N1. Okay, let's write it here, somewhere here at the beginning, because we'll use it in the application. So N1, which is the index of refraction in the first medium, multiplied by sine the angle θ1, the main angle, is equal N2 multiplied by sine θ2. We'll use this equation in case of application. Okay, so again, N2 is the index of refraction in the second medium, and θ2 is the angle of refraction when crossing the boundary or crossing the surface. Okay, let's talk about this application here. So example problem 1. Alright, so the angle of refraction. A beam of light in air, okay, so it's in the air, so this means that the n, in this case, n1 of the air, if you remember, it's approximately equal to 1, okay, hits a sheet of floating glass at an angle of 30 degrees. So the main angle, theta 1, is equal to 30 degrees. Okay, what is the angle of refraction of light? So the question is to calculate the unknown, and this question is theta 2. Okay, n2, which is for the floating glass, you can refer back to the table and you can find out that the floating glass has an index of refraction of 1.33. So let's apply this equation here. Okay, so n1 sine 1 equal n2 sine 2. So to do that, so n1, which is equal to 1 multiplied by sine 30 degrees, equal n2, which is 1.33 multiplied by sine theta 2. Okay, so the unknown, remember the unknown is sine theta 2, so you arrange the equation, or you can quickly find it out by doing shift solve on your calculators. So it's equal 1 multiplied by sine 30 divided by 1.33, okay, which is equal to, let's find out from the calculator. So it's sine 30 divided by 1.33, which is around 0.375. Okay, but remember, I'm not looking for sine theta 2, I'm looking for theta 2 alone. So what to do in this case is we do shift, it will become sine minus 1 of this value. So it will be equal to, so by doing on the calculator shift sine of this answer, so we got a 22.08 or 0.1 degree. And by the way, we are always measuring the angle referred to the normal line. Okay, so when we are talking about 30 degree here, this means 30 degree from the normal line, or 22 degree 0.1, this means that it's from the normal line. So again, all the angles calculated are always measured from the normal line. Okay. So let's solve practice problem. Let's choose, or let's go with question 2. Okay, so let's go with question 2. Okay, so as light travels from air into water, so remember that n of the air is equal to 1, and n of the water, n of the air, okay, let's consider it's n1, it's approximately equal to 1, okay, and n of the water, okay, it's approximately, if you refer back to the table, n of the water is equal to 1.33. Okay, so that's the given. Light travel from air to water. The angle of refraction, this means angle of refraction, so it's theta 2 is equal to 25 degrees to the normal, of course. Find the angle of incidence, which is theta 1. Okay, so let's apply this equation always. So n1 sine of the first angle, so n1 equal to 1 multiplied by sine theta 1, which is the unknown, equal to n2 1.33 multiplied by sine theta 2, which is in this case 25 degrees. Okay, so if we like to draw that, so let's say that's the surface between air and water. Okay, that's the separation between them. Of course, second step, first step, you define the medium, air to water. Second step, you draw the normal line. Let's say the normal line. The angle of incidence, which is unknown, okay, let's say it's that one. Okay, that's the angle of incidence, theta 1, which is we don't know yet. Okay, it's a question mark. Okay, the angle, the second angle, which is of refraction, it's deviated, of course, it will be deviated, and it's around 25 degrees. Okay, it's 25 degrees. So the main question is to calculate this angle here, theta 1. So let's go back to that question here, to the calculation. So by doing shift solve, okay, by doing shift solve on the calculator, I did it earlier, so theta 1 will be equal around to 34.2 degrees. Alright? So the angle here is supposed to be 32 or 34.2 degrees. So if you notice from the picture, the angle here is bigger. Here the angle or this ray is approaching the normal, coming toward the normal. And this is true because we are going from low index of refraction to a higher index of refraction. Let's move forward to the next slide. Okay, the meaning of the index of refraction. So again, here we are talking about now the meaning of the index of refraction. As discussed before, it describes how much light bends as it enters a medium. So when the light passing from medium to another, it's bending. So how much it's bending is described by this, the index of refraction, which is n, small n, okay? So again, light interacts with atoms in such a way that it moves slowly, okay? Because this is slow motion, when it passing from this different in speed, when passing from one medium to another medium, this create the bending or changing in direction, okay? This is described by the way in the wave model of light. That's described here. So we have the wave model of light. Okay, sorry. So it's described here. We have the incident wave or the incident light. Let's say it's moving from in the air, medium, or in vacuum. Okay, these are the waves of the light, and this is the boundary. Every time the light crossing this boundary, we have a change in speed. If you notice, this part of the wave hit the boundary first, okay, and then the other part will follow. So this difference in speed creates such deviation in the direction, and that's what we call by the incident wave and the refracted wave. Okay, both don't have the same direction. Okay, we still have a little deviation in this part. Okay, so another equation in this chapter, which is the index of refraction, which is n, index of refraction is equal to C over V. What do you mean by C? C represents the speed of light in case of vacuum. Okay, this in case of vacuum. So C again represents the speed of light in case of vacuum. Okay, which is the fastest. So the light goes the fastest were in the vacuum model or vacuum medium, and V represents the speed of light of other medium. It doesn't matter whether it's glass or water. Okay, it doesn't matter, but V is the speed of light in a very specific medium, but not in vacuum. If it's in vacuum, if V represents the speed of light in case of vacuum, so V becomes C. Okay, so C only describes the speed of light in case of a vacuum medium. Okay, so he's talking about the total internal reflection. Okay, remember, notice here we're talking about reflection. Okay, in the lesson called refraction. So what they mean by the total internal refraction? So let's before going through the text, let's look at this figure here. We have here we have a laser light underwater. as you can see here, the laser light is underwater and going from water to the air every time. So at the beginning when you see the angle, okay, as you see here in the first case, here I mean, okay, the angle is 0, so the light continues straight. The other part here, the angle is 15 degrees. It's hitting the surface and continue at, I think it's 25 degrees. Okay, then if at the angle of 30 degrees here, at the angle of 30 degrees, it continue at 42 degrees. Okay, if the incident wave here it's 45 degrees, it will continue at 70 degrees, as you see here, 70 degrees. But okay, so all of that in case of refraction. Why? Because the light passing from one medium to another medium. Let's make a small table here. Let's make a small table and let's write angle of incidence. Let's say incidence, okay, with angle of refraction. So at first we have a 0 degree here, it continue, so if the angle of incidence is 0, it will continue as 0 degree, it will continue the normal, okay, no deviation, because it's perpendicular to the surface. So that's the surface and the light is perpendicular to the surface, so making a 0 degree with the angle, so it will continue with this 0 degree. In case of 15 degree of incidence, okay, the light band at 25 degree, so it's 25. If we still increase the angle of incidence to 30 degree, it will deviate at 42. Okay, at 42. If you continue from 30 to 45 degree, if you increase the angle of incidence, the angle of refraction is 70 degree. Okay, so as you notice, the angle of refraction is bigger than the angle of incidence. But something special happening if we're still increasing the angle of incidence. Look at this. If we're still increasing the angle of incidence to 60 degrees, let's say, what are we getting? There is no refraction. Okay, why? Because the light is reflected. The light is reflected. That's why they say here in the title, it's a total internal reflection. If we still increase the angle from 30 to 45, then from 45 to 60, we don't have any refraction. We don't get any refraction. All the light is reflected down. Okay, that's what we mean by the internal reflection. So let's go back to the text now to see what they are trying to explain or telling us in this case. So the total internal reflection, okay, we have the higher n, okay, we know that from, okay, it's passing from high n, okay, so here we have higher n, a medium from higher n, okay, that's the angle of incidence. We have higher n, okay, to a small n, okay, that's the case of internal reflection, okay. So as you notice, the angle of refraction is always bigger or larger than the angle of incidence, as we draw here from the table. So again, I write here, so here large index of refraction, and here we have a smaller or a small index of refraction. Okay, so that's why you see this phenomena. So there is something happening, something interesting happening. I told you at the end that at a certain angle that we still didn't know yet, at a certain angle, okay, of incidence known as critical angle, okay, which is, they call it theta c, okay, they call it theta c. The reflected ray lies along the boundary of the two medium. That's what we call by critical angle. Critical angle. Okay, let's draw it here. Let's draw it here again. So let's say we have, that's the, let's say here we have water, and here we have the air. So here we have large N, and here we have a small n. Okay, here the n is bigger. Okay, that's the normal line as always. Okay, look how it's, how can we explain that? So that's the incident light. That's the incident light hitting the surface of the of air water. At this angle, we call it the critical angle, theta c. Okay, it's somewhere between 45 and 60, by the way. It's an angle between 45 and 60. So at this angle, what's interesting about this angle, that the light is not reflected. It will not go up. It goes, look at the sentence, at this angle theta c, the reflected ray lies along the boundary. Where is the boundary? This is the boundary. So the reflected ray goes with the boundary itself. It goes with the boundary. It goes with the boundary. It's not going up and it's not reflected. Okay, no refraction and no refraction. Okay, so at the two mediums. So that's what we call it by theta c. Okay, that's what we mean by critical angle. Theta c means representing the critical angle, and again, it's somewhere between 45 and 60 degree. Okay, let's continue. Okay, so that's the figure that I'm trying to explain here. Okay, remember this equation, I'll come back to it. Sine critical angle equal to n2 over n1. I'll come back to this equation, but just to do this explanation. So if you compare this figure, okay, to the one that I'm drawing here, to the one that I drawed, okay, so we have a critical angle going straight as here. That's the critical angle. Okay, here we have also the critical angle. It goes straight with the boundary, making a 90 degree with the normal. So this is 90 degree as well. Okay, if we would like to apply Snell law in this case, what are we getting? Again, if trying to explain or apply Snell law, n1 sine theta 1 equal n2 sine theta 2, in this case of critical angle, what are we getting? Let's see. Okay, so n1 sine 1 equal n2 sine theta 2. So n1, which is the n of the water, okay, n of the water, okay, or let's call it n2. Let's call it n2. Okay, because it's the other medium. Okay, multiplied by sine critical angle theta c equal n of the air, okay, which is n1, multiplied by sine the angle. What is the angle in this case? It's 90 degree. Okay, so critical angle, okay, we still don't know it, okay, equal n2, okay, sorry, n1, here we're talking about the air, multiplied by the other angle, which is 90 degree. Sine 90, as you know, sine 90 is equal to 1. Sine 90 degree is equal to 1. So to calculate the critical angle, sine theta c it will be equal to n1 over n2. Okay, that's the equation of the critical angle, sine theta c. So we can add it here to the table. Sine theta c equal n1 over n2. Right, so let's continue. So we are approaching the end of the lesson, talking about the mirage effect. Okay, so in the case of this effect, mostly this happen in case or in a very hot day where the temperature is so high